Shall we start again?
Okay.
Shall we start again?
Okay, sir.
Okay, sir.
Now, when you look at reinforcement, now these days we can use reinforcement having a strength of 500 newtons per millimeter squared. That is the yield strength. And those reinforcement is manufactured by using this quenched and self-tempered technology, what we call QST, quenched and self-tempered. And that's what they call it as QT bars. And the way that is manufactured is when the bars are just turned out, when it is red hot, water is sprayed on the bar so that the outer surface becomes cooler immediately. And that process actually work hardens the outer surface. And then this bar is allowed to cool gradually so that the inner portion of the bar will be at a lower strength than the outer crust. And there's an advantage of this because the inner portion of the bar is at a lower strength. It has a better ductility. So when you bend the bars, these bars generally tend to be reasonably okay because the ductility of the bar would be higher. So this is the hot roll process that is used, and they call it QT bars or QST bars, and the strength is 500. And we know the elastic modulus of steel is 200 kilonewtons per millimeter squared. So when you divide 500 by 200 and also by the partial factor for material strength 1.15, you will find that the strain at which the steel yields is 0.00217. So steel yields at 0.00217. So that is the strain at which steel yields, and concrete crushes at a strain of 0.0035. So we have a material where concrete is good in carrying compression and steel is good in carrying tension, and then we can combine them and convert it to reinforced concrete. So one of the important parameters about the concrete is the protection of reinforcement. And then you'll ask why we need protection of reinforcement. We know steel is a material that is manufactured by giving a lot of energy. So there's a natural tendency for it to undergo corrosion. And when you manufacture steel, it will form a thin ferrous oxide layer. So it will form a thin ferrous oxide layer. And when you cast concrete, we know tricalcium aluminum silicate, one of the byproducts of hydration process of cement is calcium hydroxide. And because of that, the pH value of concrete remains around 12 to 13 range. pH value of concrete is something like 12 to 13. So when pH is 12 to 13, this ferrous oxide layer is very stable. So that's why, in reinforced concrete, the reinforcement will not undergo any corrosion. But to ensure that this protection is there, we need to have a minimum cover. So we need to have a cover. The reason is, with time, the carbon dioxide in the atmosphere can start penetrating into concrete. And if you have not cured this concrete properly, gradually this carbonation will start reaching the reinforcement. And when the carbonation reaches reinforcement, the pH value can drop to about 10 to 11. And when that happens, this natural protection provided by ferrous oxide layer will be lost, because when the pH is about 9-10 range, ferrous oxide is not a stable substance. It deteriorates. So the real corrosion can start around the reinforcement, and that can lead to the rapid deterioration of reinforced concrete. So to prevent this happening, we need to have adequate cover for the reinforcement. So to determine the cover to the reinforcement, we can make use of the exposure conditions. So exposure condition is corrosion induced by carbonation, and it will all depend on the exposure type. And if you have moderate humidity and wetting and drying conditions, then you will see that most of the time the exposure condition can be XC2 or XC3 with moderate humidity, wet, fairly dry, or moderate humidity. The exposure condition can be XC2 or XC3, and if the conditions are even more adverse, then you can even go for XC4. So depending on all that, we can have the cover to the reinforcement. And generally this structural class S4 means structure designed with 50-year return period. Structural class S4 means the structure designed with 50 years of 50 years of life expectancy. So basically, we design the structure to last at least 50 years. Then the structural class is S4. And depending on the type of concrete that you are using, you can see different cover values have been specified. So depending on the exposure type, we can have different cover values. And if it is XC2 or XC3, which is the common case, we need a cover of about 25 millimeters for the reinforcement. We need a cover of about 25 millimeters for the reinforcement. In addition to this cover, the Eurocode actually specifies an additional allowance of about 10 millimeter to allow for any variations that can occur at the site conditions. So if you are not going to provide that variation, then you have better quality control and all that. The minimum cover required is about 25 millimeters. But if you want to allow for some variation that can occur at the site, you can increase this by another 10 millimeters. And then we also have to look at how do you make use of this particular table. And this table says if the working life is 100 years, of the design working life is 100 years, if you are designing the structure for 100-year duration, then increase this by 2 more classes. So instead of using 25 millimeter, use 35 millimeter cover. But on the other hand, if you are going to use concrete which is stronger, you are going to use a concrete stronger than what is specified here, then you can reduce the class by 1. So if you are using 35 megapascal cylinder strength, 35 megapascal cylinder strength, then you can reduce the class by 1. And if you are casting a slab, again you can reduce the class by 1. So here you can see, if you are casting a beam, you have to use a cover of 25 millimeter minimum. And if you are casting a slab, you can use a cover of 20 millimeter minimum. But when you allow for some variations that can occur, you might add 5 to 10 millimeters, preferably 10 millimeters, but at least 5 millimeters can be added to this, so that you can end up with 25 millimeter cover for slabs, 30 or 35 millimeter cover for the beams and other members. But if you think the exposure conditions can be adverse, then you can see you can go for higher cover values like 40 millimeter, 45 millimeter, and so on. So in foundations, because we are not very sure of the conditions, even when we use a screed concrete, we use a minimum cover of 40 or 50 millimeters. We generally use a minimum cover of 40 or 50 millimeters. And if you are using higher strength concretes, you can actually reduce the class. That means you can move this way. And if you are designing for a longer lifespan, then you have to move this way. And if you are having more adverse site conditions, then you have to move this way. So this, using these numbers, you can actually select reasonable cover values for the reinforcement. So is that clear? How to select the cover for reinforcement? And this cover is for the outer reinforcement, which is the link. So this cover is actually to the cover to the link. Is that clear? Any questions on this table? Then we'll discuss from the very basics, but quickly move to the special conditions that we have to fulfill, and also make us familiar with the various equations given in the Eurocode, so that we'll be able to use them for foundation designs. So first we'll see how to design a beam subjected to bending when the bending moments are small. When the bending moments are small. So what happens is, when you have a reinforced concrete beam, now here the link is not shown, only the reinforcement is shown. And here you can have the compression reinforcement, here S dash, tension reinforcement S. So this reinforcement will be in tension, this reinforcement will be in compression. And we know any member subjected to bending, we generally make use of some assumptions. So one of the basic assumption is plane sections remain plane. So if the plane sections remain plane, if you look at the strain diagram should be linear. The strain diagram should be linear because plane sections remain plane. And the strain in concrete is epsilon cc, And the strain in steel is epsilon st, and you can also get a strain in the compression steel, which is epsilon sc. And then we also know concrete is a weak material in tension. So because of that reason, concrete cracks in tension. So below the neutral axis, concrete is cracked. And if the strains are small, we'll be in this region of the stress strain curve. We'll be somewhere here in the stress strain curve if the strains are small. Then you can see the strain diagram is linear. If the strain diagram is linear, the strain distribution will be a triangular stress distribution. The strain distribution will be triangular like this. The strain distribution will be triangular like this. But what happens is we are not interested in finding the moment in this type of situation. What we like to know is what is the maximum moment that the section can carry. What we like to know is what is the maximum moment that the section can carry. So to determine the maximum moment that the section can carry, we have to increase the strain in concrete. So we have to keep on loading so that the stress will go up, 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 and after that, the strain will increase, and we like to see what is the carrying capacity of the beam when the concrete strain has reached 0.0035. So we like to see what is the carrying capacity of the beam when strain has reached 0.0035. So what we do is we go up to 0.0035, but when you go up to 0.0035, now you can see when you draw a strain diagram, some certain areas, the stress is constant, and after that there will be a certain region where the stress variation is parabolic, and after that you will have a certain region where the strain distribution is linear. So then you'll end up with a rectangular parabolic strain distribution. Somewhere here it may be linear, somewhere it may be linear. This region it will be rectangular, the parabolic, and here you can see it's rectangular because whatever the strain, stress is the same. Whatever the strain, stress is the same. So when you are doing the science, it's very difficult to use a very accurate stress block like this. So we actually say that this stress block is equivalent to a stress block like this, and that stress block has a depth of 0.8x, where x is the depth to the neutral axis. X is the depth to the neutral axis, and the depth of this stress block will be 0.8 times x. 0.8 times x. So this is the equivalent rectangular stress block. And when you have this, then this, we make use of this particular stress block for all our calculations. And then you also have a situation where you like to see a limiting case. And that limiting case is, we have a stress strain curve for concrete, 0.0035. We have a steel that yields at 0.00217. And these strains can be very high. So what will happen when the strain in concrete is 0.0035 and the strain in steel is 0.00217. So if you look at this situation, then we are saying when the concrete is about to crush, steel has just started yielding. Steel has just started yielding. And when you have this situation, because steel has not yielded, we do not get any warning, no warning. the member will fail at once, no warning. And that is not a good situation. So we like to see what is the depth to the neutral axis when this is going to happen, so that we can have a limit on the neutral axis to ensure that when this is 0.0035, this value will be more than 0.00217. So the first thing is to find what is this x, and you will find that 0.0035 divided by x is equal to the depth to the reinforcement is d, and that is equal to 0.00217 divided by x minus d minus x. So by using this equation, we can find the x over d ratio, and the x over d ratio that you find this way is equal to 0.617. So that means, you know, it is more than the midpoint. So the x over d value that we find this way is 0.617. So that is the limiting value. And we don't like to be in the limiting value. We like to be at a lesser value than the limiting value. So because of that reason, the maximum depth to the neutral axis is limited to 0.45d. Because of that, the maximum depth to the neutral axis is limited to 0.45d. Maximum depth to the neutral axis is limited to 0.45d. So when you consider that, this will be the kind of stress strain curve that you get. This is the strain diagram, 0.0035. Neutral axis is less than 0.45d. So because this is d, so this is less than 0.45d. And then we say the depth of the stress block is 0.8 times x, and the resultant force in concrete will act at the center of this stress block. The resultant force in concrete will act at the center of this stress block, and so there's a force this way, there's a force this way, and because there are two forces acting equal and opposite forces, these can form a couple, and that means, you know, this can be used to resist a moment. The moment resisted is equal to the lever arm, the distance between two forces multiplied by this force. So we can also find the value of FCC. FCC will be equal to 0.567 FCK, and that comes from 0.85 FCK over gamma C, where gamma C is 1.15. So when you divide 0.85 by 1.5, you will end up with 0.567. So that is the concrete strength. This is the concrete strength, means stress in concrete in newtons per millimeter squared. So if you multiply it by the breadth of the beam and depth of this, then you can find the magnitude of this force. So FCC is equal to 0.567 FCK multiplied by the breadth of the section multiplied by S, or 0.88 times x. So that is one equation. And similarly, if you consider this particular section, the section should be in equilibrium. Then because of that, you say FCC is equal to FST. The force in steel is equal to force in concrete. Force in steel is equal to force in concrete. So you'll end up with few equations. And if you look at the force in steel, we have to see where we are. And if you look at the stress strain curve, we have selected x over d less than 0.45. That means we have moved way beyond this point. So we have gone this way because the strain at this particular point is 0.00217, because x over d is less than 0.45, x over d is less than 0.45. The strain is somewhere here. The strain in steel is somewhere here. And if the strain in steel is somewhere here, then the steel has already yielded. That means we are going to, if we apply the ultimate loads, we are going to get good warning before the beam fails. So before the member fails, we are going to get a good warning in the form of cracking and deflection. And that's what we like to see. So because of that reason, we can say the force in steel is equal to the stress in steel multiplied by area. Stress in steel is 0.87 times fyk, and multiplied by the area of steel. So we know we can have an equation for the stress in force in steel. We can also have an equation for force in concrete. And we can say the moment carrying capacity is either FCC multiplied by Z or FST multiplied by Z. And FSC is equal to FST. So force in concrete is equal to force in steel. And the bending moment carrying capacity is equal to force multiplied by the lever arm of the couple. And that is Z. So when you are designing a reinforced concrete section, our main task is to find the reinforcement quantity needed in tension. So we like to see how much reinforcement area is needed. And that's what we do in design. So we can say, if we know the lever arm, we can straight away find the reinforcement needed. So the ultimate design moment on the section is M, and it must be balanced by the moment of resistance, and also need to have the force equilibrium, that is FST is equal to FCC. And then we can say the moment is equal to FCC times Z or FST times Z. And if you look at FCC value is the stress in concrete. Stress in concrete is 0.567 FCK multiplied by the area of the stress block. Area of the stress block is 0.8 times X or S multiplied by the width of the section, B times S. And then we also can say Z is equal to D minus S by 2. Z is equal to D minus S by 2, which means S is equal to twice D minus Z. So in this equation, instead of S, we can substitute twice D minus Z. So FC is equal to 1.134 FCK. That is 0.567 multiplied by 2 is 1.134. Here S is twice D minus Z. So 0.567 multiplied by 2 FCK D minus Z multiplied by B. So that is the force. And if you want to know the moment, you have to multiply the force by Z, then you will end up with this. And you can see this is the second order equation because we have D minus Z multiplied by Z. So if you divide this by M over 1.134 FCK BD squared, then you will find you can take Z this way and divide it by D, then you will get Z over D squared minus Z over D plus K is M over FCK B D squared. And here we divide the whole both sides by 1.134 FCK BD squared. So you will ultimately end up with K over 1.134. So this is a second order equation. And the second order equation, the solution is x is equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. So once you substitute in that equation, we can straight away find the value of z, and the value of z is given by d times 0.5 plus square root of 0.25 minus k over 1.134. So, which means if you know the bending moment acting on the section, if you know the width of the section, if you know the depth to the reinforcement, that is D, if you know the type of concrete you are going to use, that is FCK, whether it's 25 or 30, if you know all those, that means all the parameters in this particular equation is known, and that means this K is known. If you know K, Z is known. So that's how we find the value of Z. And when you know the value of Z, the bending moment is given by Fst times the force in steel multiplied by Z, and then that is 0.87 Fy is multiplied by Z. Moment is known. Fy is 500. Z is known, that is as a function of the depth. Then you can straight away find the reinforcement needed. So I explained this just to make it complete. I'm sure most of you are very familiar with all this. But there are certain parameters that we have to be little familiar with. That is, the maximum depth to the neutral axis is 0.45d. And so if x is equal to 0.45d, then you can calculate the value of z. And z is equal to d minus s by 2, d minus s by 2, and z is equal to d minus s by 2. S is 0.8 times x. S is 0.8 times x. S is 0.8 times x. So S is equal to twice d minus z, or z is equal to d minus s by 2, and s is equal to 0.8 times z, 0.8 times x, and x has a maximum value of 0.45. So once you substitute the maximum value of x in this equation, you will end up with this equation, d minus 0.8 times x, and that is 0.45 times d divided by 2, and d minus s by 2, and you will find that z is equal to 0.82 times d. So when x is maximum, we can say when x is maximum, z is minimum. So if x is smaller, if s is smaller, then z will be a higher value. When x is maximum, s is maximum. So when x is maximum, z is minimum. When x is maximum, z is minimum. So then the minimum value of z will be 0.882 times d. The minimum value of z is 0.82 times d. The maximum value of z is considered as 0.95 times d, because if you allow a d value, z value greater than 0.95 d, you'll find that this compression area is very thin, and when the compression area becomes very thin, there's a danger. And that danger is, crushing of concrete, because when you cast a structural member, because we are using wet concrete, the concrete at the top part of the member tend to be slightly weaker. The reason is, when you are vibrating the concrete, all these aggregates will settle downwards, and the concrete at the top tends to be slightly weaker, and that concrete can easily crush because it's slightly weaker than the rest of the concrete. So because of that reason, we limit the maximum value for Z as 0.95 times D, so that we'll end up with a reasonable thickness for the concrete at the ultimate limit state. To ensure that we have a reasonable thickness, we go into these limits. So then we have a maximum value of 0.95D, minimum value of 0.82D for Z. So then, can I ask you a question? When can you get the maximum moment carrying capacity in this section? The moment carrying capacity of this section will be maximum when we have the maximum value for X. And the maximum value for X is 0.45D. So when X is equal to 0.45D, we'll have the maximum moment carrying capacity of this section. And when X is equal to 0.45D, Z is equal to 0.82D. And then the area of this concrete will be 0.8 times X times the breadth of the section multiplied by the stress. So when you do that, you can see the stress is 0.8 times X multiplied by B multiplied by 0.82D. Then you will end up with this equation, which is a very useful equation because it will tell us the maximum moment carrying capacity of a section when we are having only the tension reinforcement, or we call it singly reinforced. So we can find this equation. MS max is equal to 0.167 FCKBD squared. And from that, we can see that we can easily find whether we can design it as a singly reinforced member. So let's have a look at few examples fairly fast. Find the reinforcement requirement for a beam of section 500 millimeters of overall depth and 250 millimeters of width, and cover to reinforcement is considered as 35 millimeters, and the links will be 10 millimeter bars, and the main reinforcement could be with H20 bars. So here I have considered 35 millimeter cover, considering that we are using 25 megapascal concrete, and we are having X2, X3 exposure condition, 50 years of design life. So we are having 25 millimeter cover plus 10 millimeters to allow for any variation at the construction site. So you will end up with 500 millimeter width, the depth, 250 millimeter width, 35 millimeter cover, plus 10 millimeters for the link, 20 millimeter reinforcement. Then you can find the effective depth of the section. That is 500 minus 35 minus 10. 10 is the link, 20 is the diameter, 20 divided by 2 is the distance to the center of the diameter of the longitudinal reinforcement. So you'll end up with 445 millimeter as the maximum depth, maximum value for D. And then what you do is, we find MOFCKBD squared for a bending moment of 185 kilonewton meters, 185 into 10 to the power 6 divided by the strength of concrete 25, and 250 is the width of the section, and depth squared is 445 squared. And when you calculate this value, you can see it's less than 0.167, which means the section can be reinforced only with the tension reinforcement. No need to use any compression reinforcement. And On the other hand, we can easily find whether what is the value of moment. Moment is equal maximum moment, or we call it imbalance, because the max when the depth to the neutral axis is maximum, we call it a balance section. So the idea of the balance section is when the concrete crushes steel yields. But here, you know, because we have a maximum limit of 0.45, we have a slightly different situation, but still the maximum moment carrying capacity is sometimes termed as imbalance. So you can find what is the value of imbalance. That is 0.167 into FCK BD squared. And when you do that, you will end up with a moment which will be greater than 185. On the other hand, you can calculate M of FCK BD squared and then show that it is less than 0.167. So this is an important equation, 0.167 FCK BD squared. So now we know we need only the tension reinforcement. So we can make use of this equation and find the value of Z, and that is this equation. Z is equal to this. So we can make use of this equation, and the value of K is 0.149, and all the other parameters are known. And then when you calculate this, you will end up with 0.25 minus 0.149 divided by 1.134, and you take the square root of that plus 0.5. So you'll find that the depth to the neutral axis, lever arm is 0.844D, or 0.844 multiplied by 445, and that is 375 millimeters. 0.844D O is the Z value. So once you multiply that by the value of D, which is 445, you'll end up with 375 millimeters as the answer, 375.7 millimeters. Then what you do is, we know the Z value, and we have this equation, M is equal to FST times Z, or we have this equation, the moment carrying capacity is equal to force in steel multiplied by Z. So you'll end up with 0.87 times Fy multiplied by A times Z, where the value of Z is known. Fy is 500, the moment is 185. So straight away you can find the reinforcement requirement, and the reinforcement requirement is given by M over 0.87 Fy times Z, and you'll find that the reinforcement requirement is 1134 millimeter squared. And if you are going to provide 20 millimeter bars, you can divide it by 314, because the area of each 320 millimeter bar is 314 square millimeters. From that, you can work out the number of bars required. So we have to provide 4 bars to develop a moment of resistance in excess of 185 kilonewton meters. Now, is that clear? And the most important parameter that we have seen here is this, because this tells us whether we can have the beam as singly reinforced or whether we need compression reinforcement. If the moment is in excess of this value, then we have to provide additional reinforcement. Any questions on this? Then you'll ask why it's important. Because when you are doing foundation designs, certain times you will find that you are actually dealing with fairly high loads, and sometimes this can be useful. And then When you are dealing with foundations, again, you might be dealing with very thick foundations. Then you'll find this limit is important. 0.95D is important. So then shall I move on to this next section, that is doubly reinforced sections. Any questions on this? I'm sure you are all familiar, but we'll quickly cover these things because some of these equations we'll be using later when you are doing the various foundation designs. So now I'll move on to this doubly reinforced section, and so basically when the moments are higher, the depth to the neutral axis x is equal to 0.45D. We cannot increase this, and we have provided the reinforcement for this. And if the still we have to carry a higher moment, there's only one way that we can do that. That is by providing additional reinforcement here and here. And if this additional reinforcement is dash, then the moment carried by this reinforcement is equal to 0.87 Fy times S dash multiplied by the lever arm. This time the lever arm is fixed, and this, let's say this distance is D dash, this is D, so this distance is D minus D dash. So it will become D minus D dash. So this additional moment is actually carried by the reinforcement because concrete can't carry any more force. And because of that reason, we cannot increase the originally provided reinforcement. Only way that we can carry extra moment is by providing additional reinforcement. So whatever the reinforcement that you provide here to carry the moment, the same amount of reinforcement should be provided here as well. Then we can develop the additional moment in the form of steel, this additionally provided steel yielding in compression and tension, and that also carrying an additional moment. So that's the theory. So if it is a doubly reinforced section, then you'll find the total M is given by 0.167 FCK BD squared plus 0.87 Fy S dash D minus D. So this is the moment, that maximum moment that can be carried as singly, and this is the extra moment that is carried by W. So we say the beam is doubly reinforced and the total moment carrying capacity is given by this equation. So you get this equation where this gives the moment that can be carried as singly reinforced, and this gives the moment that is carried by the additional reinforcement. And once you rearrange this, you can say S dash is equal to M minus this component divided by the remaining part of this component. So that is 0.87 Fy D minus D dash. And I said that, 0.167 is called K balance sometimes. So it can be K balance FCK. And the value of K balance is 0.167. So on the other hand, we can calculate this value and then say M minus M maximum divided by this. Then we can find the amount of reinforcement needed. And to calculate the amount of reinforcement needed to carry the tension as singly reinforced. We can, if you want, you can consider the equilibrium of the section. And equilibrium of the section says whatever the horizontal forces should be in equilibrium. So the horizontal forces are FSC and FCC, and these two forces, compression in concrete, compression in steel, should be equal to tension in steel. So tension in steel is 0.87 times Fy times area, force stress times area. Force in compression steel is 0.8 times Fy times As dash. So this is known. This is what we want to find. And the force in concrete is given by X is equal to 0.8 times D. X is equal to 0.45 times D. So X is equal to 0.45 times D. S is equal to 0.8 times X. So that is the depth of the stress block multiplied by the breadth of the section multiplied by the stress. Stress multiplied by area will give the force. So this is the force in concrete. This is the force in compression steel. This is the force in tension steel. So the area of tension steel can be found straight away. And when you multiply 0.567 by 0.8 by 0.45, you will find that the answer is 0.567 multiplied by 0.8 multiplied by 0.45. The answer is 0.204. So this becomes 0.204 FCKBD, and you have to divide this by 0.87 Fy, so you get 0.87 Fy in the denominator. So this way you can straight away find the reinforcement requirement for a beam carrying a moment in excess of the maximum that can be carried as singly reinforced. So you can straight away find the area of compression steel and area of tension steel when the section is having a moment in excess of what the section can carry as singly reinforced. So we consider the condition that when the section is having a moment more than the singly reinforced moment carrying capacity, all the excess moment is now carried only by the additional reinforcement provided. So you'll end up with this equation, but there's a small check we have to make sure. We have to carry out a small check to assure that the use of this 0.87 Fy times As dash is actually correct. So we have to carry a small check, and the check is that the steel has actually yielded. And for the steel to yield, the strain at this level should be more than 0.00217, and that is the strain that we got from the stress strain curve. So because of that reason, we say for this to be true, this should be more than 0.00217. So you can use the similar triangles, 0.00217 divided by x minus d dash, and x is equal to 0.45d minus d dash is equal to 0.0035 divided by x, which is 0.45 times d. From this, we can find the d over d dash ratio, d dash over d ratio, and d dash over d ratio is 0.171. So you select the cover and you select the link diameter, you select the bar diameter, So once you select the cover, link, and bar diameter, you know the value of D dash. We also know the value of D. We can always find D dash over D ratio. And when we know D, we can find the corresponding D dash. And if the reinforcement that you provide is too much inwards, then you might find that the strain is less than 0.00217. In that case, the use of this equation is wrong, because in this equation we have already assumed that all the compression steel has yielded. So you have to be a little careful there. And this is not a major problem in most of the cases, because generally, you know, when you have a beam having heavy loads, this can happen only if the beam is carrying heavy loads. And if the beam is carrying heavy loads, it's unlikely to be very shallow. If you have at least 500 millimeter depth, then you can see this equation gives 0.171 multiplied by say effective depth of 150 gives an answer of about 77 millimeters. So if you are going to provide this compression reinforcement within these 77 millimeters, then you are assured that the compression reinforcement has already yielded. But if you are going to have this compression reinforcement below 77 millimeters, then you have to have extra reinforcement, because you are providing the compression reinforcement too much inwards. But this is not a real problem, because most of the time when the beams are heavily loaded, we make sure that the depth of the beam can be more than 500 millimeters. But if you are having a very shallow beam carrying heavy moments, then you have to be careful here. So now we repeat the same problem with a moment of 285, and that also shows the advantage of reinforced concrete. One of the main advantages of reinforced concrete is that you know, for the same section you can carry heavy loads or light loads. So when the loads are light, we'll lightly reinforce it. When the loads are heavy, we can have more reinforcement, and we can even go for doubly reinforced section. So concrete sections, you can have a wide variation in the bending moment that can be carried by a given section. So shall we take a 10 minutes break and again start at 4:15? And then I will explain the next problem. So we'll take a break now.